In this video, we're going to do some guided exam question practice on multiple questions that have come up on radioactivity. Now, radioactivity often just comes up as some short questions. So these are usually 6-mark questions that come up in question 4, and you're talking maybe 2 to 3 minutes to do each of them. So we're going to go through 7 different questions here. So I'd say set your timer for approximately 15 to 20 minutes. Okay, we'll go with 15, see if we can get them done. They don't take that long. Set your timer for 15 minutes and let's get started. Okay, all right, let's look at the first one. I'm not sure exactly what year it came up. I didn't mark it, but we're going to walk our way through it. So it says, first of all, what change? So they're looking for you to just say what change takes place. And we're talking about for the nucleus. What change takes place in the nucleus of an atom when beta decay occurs? So you have to know exactly what beta decay is and specifically refer to the changes in the nucleus. So we're going to go ahead and we're going to write that down. We'll write nucleus. And again, you should do this as well when you're doing your practice. Keep in red at the side what the main idea is. And we're talking about the changes to the nucleus during beta decay. All right, so I'm going to get you to pause the video now and describe what happens to the nucleus during beta decay. Do that now. Okay, so you should only be watching if you've written down what change you think happens in the nucleus. Well, during beta decay, a neutron from the nucleus splits into a proton and an electron, and then the electron gets fired out of the atom. So we're going to say that. A neutron, so a neutron splits into a proton and an electron. That's what we should have said. And then probably the final end bit of the answer, describe what happens to the electron. So pause the video and describe that now if you haven't done that already. Okay, we might say that the electron is emitted. So an electron which is emitted. Now, to be honest with you, if I was being 100% honest, I think most years you would probably get the marks just for this bit. A neutron splits into a proton and an electron, but it's always good for you to clarify what actually happens to that electron. It doesn't stay there, it does get kicked out. All right, that definitely took us less than 2 minutes. Let's move to the next one. Write a balanced nuclear equation for the beta particle decay of the francium-223 nucleus. Okay, so we're asked about beta decay. So again, we must know what happens during beta decay. All right, so I'm going to help you lay this out. This is a beta decay equation. This is what we're doing, beta decay equation. And again, if you don't remember these, it might be worth your while to go back and a quick look over the video that we did on them. All right, so the first thing we want to do is write down what we began with. We began with this thing here. So this was important from the question. We began with francium. Francium 223 was the mass, and the atomic number of francium is always 87. Okay, and we're asked to write a beta particle decay equation. Right, so for a beta particle decay equation, we are going to produce something on the other side. Now, I'm going to draw some boxes here for you guys to fill in. Okay. So what's missing from these boxes are some symbols and some numbers. So this here should help you to fill in and get this correct. So what I want you to do is pause the video and write this out and fill in the boxes if you can. Okay, right, so you should only be playing if you have done this already. If you didn't know how to get it started, I'm going to begin by writing what always happens in a beta decay equation is we produce a beta particle. So we produce a beta particle. So this here is the symbol for a beta particle. So you should always produce that in beta decay equation. The mass, I want to put the mass of a beta particle here. If you didn't already do that now. All right, well, a beta particle is just an electron, so its mass is negligible. We're going to put it as a 0. It doesn't have any mass. And down here, we're going to put the charge. Pause the video, do that now if you haven't done it already. All right, so a beta particle has a charge of -1 and it has a mass of 0. Okay. So now that we know this, we need to work out what happened over here. So you've got to put in a symbol. If you didn't notice, this is going to be the symbol of an element. It's not going to be the same element as this because the nucleus has changed. So pause the video and write down what you think it is. All right, so hopefully you worked out what happens. If you didn't, I'm going to give you another clue, another little bit of help here. And remember, trying to think about what happens before and after. So before beta decay versus after beta decay. Well, what happens is a neutron, we said it in the definition above, a neutron splits into a proton plus an electron. Okay, so if we're thinking about before the beta decay, we had an atomic number of 87. So that meant we had 87 protons plus, well, how many neutrons did we have? Well, it's 223 take away 87. So we would have had plus 136 neutrons. And what do we know happens in beta decay? One of the neutrons turns into a proton and an electron. So that means we're going to have 88 protons at the end because we produced a new one. And that number is going to have gone down to 135. 135 neutrons. Now, if we were to add up the two numbers here, we would get 223 will be the mass here, but 223 will be the mass over here as well. So the mass has not changed, but what has changed is we have an extra proton. So now that you know that and we've recapped that, go ahead and fill this in for me. Okay, so hopefully you have filled it in like this. The new atomic number is going to be 88. Okay, so 88 is the new atomic number. The mass number hasn't changed because we've still got the same number of protons and neutrons total, 223. And sorry, that isn't very clear, but it is 223. And this is obviously a new element, new atomic number 88. So what will this element be? This element is radon. Okay, so well done if you got that right. Good job, that is it correct. Right, that might have took us a little bit longer than 3 minutes, but I was doing quite a lot of extra explaining. Okay, so you get another chance now to practice because this is a similar question underneath. Write a balanced nuclear reaction for the beta particle decay again. This time it's iodine 131. So I'm not going to help you lay it out this time. You've just done one, so you should be able to do it. I will help you get it started. I131. Right, the first thing you're going to have to do is you're going to have to go to your periodic table and find the atomic number of iodine and write it down here, and then go ahead and finish off the rest of this. So pause the video and do that now. All right, so if you couldn't find it or you couldn't get it started, I'm going to give you a little bit of help here to try and get it started. So iodine has an atomic number of 53. Okay, so again, if you weren't able to, you should have been able to now, but if you weren't able to, I'll give you the boxes to help you get started. Okay, so we're going to produce something. I'm going to produce something else over here. If you're not sure, look back how you did the last one, but this should be pretty automatic for us now. Pause the video and finish it off. All right, so again, this is beta particle decay. This is beta particle, so we're going to produce a beta particle. Here it is, there's a beta particle. What do we want to do? Our mass of our beta particle is always 0 because just an electron and a charge is -1. All right, so now think about what's happened to the nucleus. What's gonna be the result over here after the beta particle decay? Pause the video, do that now. Okay, so what we know is that a neutron N splits into a proton plus an electron. Remember that? Okay, so here is the electron, the beta particle. The proton stayed in the nucleus. So what happens to the atomic number? Hopefully you realize that the atomic number is going to go to 54. What will happen to the mass? Well, a neutron's just turned into a proton. They both have the same mass, so the mass has stayed the same, 131. And the new element, if you look it up, what's the element with the atomic number 54? If you didn't know to do that already, go pause the video, go do that now. All right, so hopefully you got that the new element is xenon. Okay, so Xe xenon. All right, well done if you got that right. All right, the next one, what does it say? It says give. So it's just literally asking you to give the names or just a couple of words. You don't need to write much paragraphs. Give two. Make sure we do two. Two properties of alpha particles. Okay, so two properties. And it's for alpha particles. So any two properties, any two features are described that help us describe alpha particles. Pause the video and write down two properties of alpha particles now, please. Pause the video, do that now. All right, very quick revision. If you don't remember what an alpha particle is, if you weren't sure, I'm going to help you think about that now. Okay, so an alpha particle is essentially a helium nucleus. And what that means is it's a particle made of these four smaller particles. Okay, now hopefully this is reminding you of something. The four particles here, two of them are blue ones, and these are two protons. And the other two particles are two neutrons. So an alpha particle is a particle made of two protons and two neutrons. Okay, so some features of this might be the mass and the charge of this particle. So looking at this diagram, if you weren't already able to write down properties of these, write down two properties now that you've seen how many particles are in here and which particles they are. Write down the mass and the charge. Do that now. Pause the video. Okay, so the two easiest properties here to remember are, well, there's two protons and two neutrons. There's no electrons to balance out the charge. So overall, that means that this thing is going to have a +2 charge. So that is a property. That's one of the things you could say. There's lots of resulting properties of this, by the way. You could have said that they are deflected by electric fields. So deflected by electric fields, and this is because it has a charge. It will be deflected by electric fields. So that's a reasonable property. Or sorry, by electric or magnetic fields. Electric or magnetic fields. So that means it will be attracted to a magnet. What about its charge? Well, it's got two protons and two neutrons. So in AMUs, atomic mass units, what will the mass be? Pause the video, write that down. Okay, so we're going to say a mass of 4 AMUs. It's got two protons, two neutrons, mass of 4 AMUs. Okay, so, and again, that's another property. So either those two, or you could have this one. Okay. Also, well, what's a resulting property because of its mass is that it would have a high ionizing power. This is something we learned about when we talked about alpha radiation. It has a high ionizing power because it's got the biggest mass out of all of the radioactive radiation, essentially. If this here is an atom that we're drawn and these are the electrons, well, if we were to fire an alpha particle at it, an alpha particle has quite a big mass, so it has the ability to knock electrons out of the atom. So we call this the ionizing power. So that has a high ionizing power. That's essentially another, and there are lots of other ones that you might have talked about. Those are some of the main ones that we did. All right, next question, let's look. It says, in November 2006, former Soviet agent Alexander Litvinenko died in London. Okay, so interesting that this here was a topical issue at the time. I don't know if you're probably too young to remember it. So well, this would have been in 2006, or maybe 2007 paper, the one the year after. And I suppose it was a topical issue, something that was happening in the real world at the time, where someone essentially used radioactive material to poison an ex-Russian spy, essentially. Okay, this happened in England. So because it was in the news at the time, it was topical, they put this in. Is it important? Not really, to be honest. It's just a distraction. It's just a bit of background. There's not really much important in here that I can tell. We definitely don't need to know anything about his name or that he died in London. Again, it's just a distraction. The cause of his death was identified as radiation poisoning by polonium-210. Now, to me, that's going to be important, I think. We might be talking about this later, but the rest, not really. What does it say here? Polonium-210 decays emitting an alpha particle. So it's alpha radiation, okay? So if it's an alpha particle, that means it's alpha decay. That's going to be important, I think, later on. Copy and complete the equation for the alpha decay of polonium-210, filling in the values of X. So it wants us to fill in the atomic number, Y the mass number, and Z the element symbol. All right, so all that blurb, and really all they want us to do is write this alpha decay equation and fill in this section of it here. So a lot of our nonsense, to be honest, to distract. But what they want is they want us to write an alpha decay equation. So we all know how to do that. Even though there's new stuff in this question that we've never seen before, it doesn't matter. It's only a distraction. What they really are interested in is, can you figure out that what you've got to do is write an alpha decay equation for this here? And they even give us some of it, which is nice. So we've got polonium-210, 84, gives you, I'm going to leave that. I'm going to put boxes in instead for you guys to fill in. Okay. And then they even give you this, that it's a helium nucleus and it's got a mass of 4, an atomic number of 2. All right, so again, I think most of you probably remember how to do this. Remember, if you're firing this out, then this is missing from over here. Okay, so this is, you've got to essentially take away the mass and the number of protons of this particle that's been fired out of the nucleus. So what's going to be left here? What's left? So pause the video, work that out, fill it in. Do that now, please. All right, so hopefully you can see that, well, this is the atomic number, okay, down the bottom here. So this here is the atomic number, and so is this atomic number. Well, the atomic number has lost these two of the alpha particle, which means that 84 is now going to be 82. Okay, and it's also lost a mass of 4. And the reason why it lost a mass of 4 is because there were 2 protons and 2 neutrons. So this is the mass. So this is the mass of the original. This is the mass that's now missing. So here we're going to have to take away. I mean, this stuff is really easy for us if we practice a few of these. 210, take away 4. We now have 206 left as the mass. All right, so which element is this? If you didn't already do this, pause the video and work it out. Which element is the element atomic number 86? Okay, so you should have worked out that this is radon. Okay, so pretty easy stuff, I think. I've just double checked that it is radon 80. Oh, it's not, sorry, radon is 86. So I didn't check that properly. I'm going to go to my periodic table again. It's 82, it's lead. PB. Sorry about that now. And that was just from me not checking carefully. So it's always a good idea to go back and check again. All right, so well done if you got those right. Okay. Next question, give 2 differences. So just give, and so we don't have to go into too much detail, right? 2 differences between nuclear reaction and a chemical reaction. All right, so anytime I'm asked for 2 differences like this, I always think it's a good idea to lay it out. You've seen me do this before, lay it out as a table to compare them, okay? So here we're gonna put chemical reactions, and here we're gonna put physical changes. No, not physical, sorry. Nuclear reactions. Sorry, I'm thinking of something from the junior side. Nuclear reactions. So we've got chemical reactions and nuclear reactions. Okay, so if you're confident that you can do this by yourself, pause the video and put in the 2 differences now, please. Okay, so you should have one here and compare them, and you should have another one here in blue, and you should compare them based on that thing. Okay, so pause the video and do that now. All right, so if you're not sure, if you can't remember, I want you to tell me what part of the atom does each of these involve. So for here, which part of the atom does each of these involve? Fill that in on the top dot here if you weren't sure. Okay, so nuclear reaction, chemical reactions, these involve the electrons, and it's specifically the orbiting electrons. So involve the orbiting electrons. These are the electrons outside the nucleus. Orbiting, orbiting electrons. These are the things that interact with each other in chemical reactions, whereas nuclear reactions involve the nucleus. They involve the protons and the neutrons. Very different type of reaction involve the nucleus. All right, which one of these creates new elements? Pause the video and include that if you did not already. Okay, so hopefully you said that chemical reactions do not create new elements. No new elements. You do not change the element. You make something called a compound. Whereas nuclear reactions, these make new elements. So one nucleus can turn into the nucleus of another element. New elements made. Which one of them releases nuclear energy? Pause the video and include that now. All right, so obviously the nuclear reactions involve the release of nuclear energy. So releases nuclear energy. Whereas this one, no nuclear energy. Now you see I've done 3 differences here because it's just a good idea in case they're not accepting one of these from you, okay? But only put in a 3rd one if you're sure it's right, because if you put in 2 right ones and you put in a wrong one then that's really badly wrong, they might cancel out one of your right ones. So I'm putting in 3 because I'm pretty sure they're all right. I'm just worried that maybe one of them they mightn't be accepting this year, but I'm only putting them in if I know that they're right. Right, last one. Okay, so all it says is to list, make a list. That's all you have to do. List the following 3 types of radiation in order of increasing penetrating power. Now they've underlined increasing because they want you to notice that. So penetrating power in order of increasing. What that means is start with the least penetrating and work the list up to the most penetrating. Okay, so making a list, I'm going to make 3. I'm going to put the 3 with commas in between them like this. I'm going to put the least penetrating to the most penetrating. That's what they want you to do here. So pause the video and put these in order of least penetrating to most penetrating. Do that now. Okay, well, actually, it's crazy funny here that it actually works out to be the order they're already in. Okay, just, you know, alpha, beta, and gamma, that's the order that they are actually in. So alpha particles is stopped by literally a few centimeters of air. Beta particles, a few pieces of a few sheets of paper or a few sheets of tin foil. And then gamma radiation needs like quite a bit of like lead or concrete, so much more penetrating. So least is alpha, next one is beta, and the most is gamma. Right, so hopefully you can see that those questions on radioactivity are very manageable. I would even go as far as to say as they're nice. And, you know, sometimes it comes up as a half question, half a full question, and it's really not a bad question to get. So hopefully you agree, and I'll see you in the next one.